Before the scientist appears a chaotic signal. Its oscillations rise and fall without obvious structure. At first glance, the waveform seems random, but hidden inside the noise may exist meaningful patterns waiting to be discovered. The scientist asks a fundamental question. How can mathematics detect invisible structure inside complex data? A second waveform now enters the experiment. This smaller pattern acts as a detector. As it slowly slides across the signal, the computer continuously compares their shapes. Convolution begins by moving one function across another through time. At every position, the local interaction between the two waves is measured. When the detector overlaps the signal, their values are multiplied together. Where the patterns align, the products reinforce one another. Where they disagree, positive and negative contributions begin canceling out. The computation transforms geometry into measurable interaction. Convolution is now evaluating how strongly the two patterns resemble each other locally. The computer now adds all overlapping contributions together. Thousands of tiny interactions combine into a single output value. That value becomes the convolution result at this position. Then the detector shifts again, and the process repeats continuously. From repeated local comparisons, a new signal slowly emerges. The scientist now replaces the detector with a smoothing filter. As convolution scans across the signal, rapid fluctuations begin disappearing. Random noise fades away while the underlying structure remains. What once appeared chaotic now reveals a cleaner hidden waveform. Convolution has become a mathematical tool for extracting order from noise. The process now moves beyond one-dimensional signals into images. A convolution kernel scans across pixels throughout the digital picture. Edges become visible. Boundaries sharpen. Hidden visual structures emerge automatically. Modern computer vision systems and neural networks rely on convolution to recognize patterns inside images and video. The scientist now applies Fourier analysis to convolution itself. A profound simplification suddenly appears. In frequency space, the difficult sliding operation transforms into simple multiplication. Filtering, communication systems, audio processing, and image compression all become deeply connected through this mathematical relationship. The scientist observes convolution appearing everywhere across science and engineering. Inside medical imaging, wireless communication, artificial intelligence, physics, and biological systems, the same mathematical principle quietly emerges again and again. Convolution describes how structures interact across space and time. It transforms local overlap into global understanding. And through this simple sliding process, hidden patterns inside reality become visible.